In this video, we are going to talk about discrete dynamical systems and how eigenvalues and eigenvectors can help us understand their long-term behavior. We are going to start with this overview slide and spend maybe 3 or 4 minutes, and after that, we'll go through each topic in more detail and with more examples. We are going to look at dynamical systems that can be described by the difference equation. The vector x of k plus 1 is equal to a times x of k, where the vector x of k gives information about the system as time denoted by k passes. So the next time unit is equal to a times the previous time unit. We can use our set of eigenvectors as a basis for Rn, and then we have an initial vector x naught, which can be written as a linear combination of our basis vectors. Then when we want to calculate x of 1, for example, that's a times x naught. Since x naught is a linear combination of the vectors, we rewrite that in this way. We've rearranged, pulled out the c1, the constants in front, and then we have a times v1 and a times all the eigenvectors. But since these are eigenvectors, our a v1 is simply equal to lambda v1, and our a v2 is simply equal to lambda v2. When we look at this pattern, we have this equation then for x of k. It's equal to c1 lambda 1 raised to the k times v1 plus c2 lambda 2 raised to the k v2 up to cn lambda to the n raised to the k vn. We will look at the graphical description of solutions for 2 by 2s. And the thing about this, as k approaches infinity, so if our lambdas are less than 1 in magnitude, these terms will then be going to 0. So the origin will be an attractor when both eigenvalues are less than 1 in magnitude, whereas the origin will be a repeller when the eigenvalues are larger than 1 in magnitude, because if the lambdas are larger than 1, then these terms will continue to grow and they'll go away from the origin. And the origin is a saddle when one eigenvalue is less than 1 and the other is greater than 1 in magnitude. We talk about a change of variables for non-diagonal matrices. So if A is not a diagonal matrix, it is similar to a diagonal matrix, as we have seen in our previous video, and we consider this a change of variables. So instead of x of k plus 1 equals ax, we define a new sequence y sub k, which is equal to p inverse x of k. Finally, we will look at the long-term behavior of dynamical systems with complex eigenvalues. So that concludes our quick overview. So we'll start again by looking at eigenvalues and eigenvectors and dynamical systems. We will be looking at dynamical systems that can be described by a difference equation given here, which is a vector equation where the vector x of k plus 1 is equal to a times the vector x at k. So the vectors x of k give information about the system as time, which we denote k, passes, where k is a non-negative integer. We will start with our initial vector x naught, and then x1 is equal to the matrix A times x naught. And x2, the next time step, is equal to a times the previous time step, x1. In this way, we're going to get a sequence of x of k's. All but our last example will assume A is diagonalizable with n linearly independent eigenvectors and corresponding eigenvalues. For convenience, we'll assume the eigenvectors are arranged in order of increasing corresponding eigenvalues. So we have our v1, v2 up to vn, and since they're linearly independent, and that is always going to be the case if A is diagonalizable, then we're going to have a basis for Rn. So any initial vector x naught can be written as a linear combination of the bases. So x naught then will equal to some constant times v1 plus a constant c2 times eigenvector v2 up to cn times eigenvector vn. And this eigenvector decomposition of x naught determines what happens in this sequence x of k. And that's because x1, when we calculate x1, that's a times x naught. So a times x naught is a times this linear combination here, and I just kind of pulled the c1 out in front because that's allowable in vector multiplication. You can pull out constants. But now, because this is an eigenvector, our AV1 is equal to lambda V1, lambda 1 V1, and our AV2 is lambda 2 V2 up to AVN is lambda n Vn. X2 then is equal to A times X1, so we have A times our X1 from our previous step. Then we're going to factor out our constants, so we have C1 lambda 1 times A times V1, factoring out our constant C2 lambda 2 times A times V2, up to Cn lambda n A times Vn. And similarly, because V1 is an eigenvector, this AV1 is going to be equal to lambda 1 V1, and AV2 is lambda 2 V2, and AVN is lambda n Vn. So what we get is C1 lambda 1 squared V1 plus C2 lambda 2 squared V2 up to Cn lambda n squared Vn, which means our kth, x to the k, is equal to C1 lambda 1 to the k V1 plus C2 lambda 2 to the k V2 up to Cn lambda n to the k Vn. Now looking as k gets large, as long as these lambdas are less than 1, these lambdas to the k are going to go to 0. If these lambdas magnitude are greater than 1, that's when these will get large. So for example, if lambda 1 is greater than 1, and all the other lambda j's for lambda sub j is less than 1 for j greater than or equal to 1, so all of these, the magnitudes are less than 1, then as k gets large, we'll find that x of k, these all go to 0, and we're only left with C1 lambda 1 to the k V1. The discussion of our formula for x of k and what happens as k gets large has been summarized here. So next we'll do an example with populations. And I do want to mention there are other applications that are very engineering oriented, except that then we'd have to be talking a lot about the background of the engineering. So population models are often used because they're the easy ones to understand right away. Here is our summary, our x naught, and our formula for x1, and then x of k. So our example says we have a predatory prey system, and we denote the owl and wood rat population in time k, or at time k, by the vector x of k is equal to O of k and R of k, where k is the time in months, O of k is the number of owls in the region studied, and R of k is the number of rats measured in thousands. So suppose O of k plus 1 is equal to 0.5 k O of k plus 0.4 R of k, and R of k plus 1 is equal to minus p times O of k plus 1.1 R of k, where p, this p over here, is a positive parameter to be specified. I'm just going to write my x of k. Now I have my owl population and my rat population, and x of k plus 1 is, the O of k plus 1 and R of k plus 1. And then I have these equations that tell me what O of k plus 1 is equal to, and the equation that tells me what R of k plus 1 is equal to. So looking at my O of k plus 1, this 0.5 here says that if this R of k is equal to 0, that tells me that if we had no rats for food, only half of the owls would survive each month. While over here, if we had no owls, so let O equal 0, the 1.1 R in the second equation says that with no owls as predators, the rat population would grow by 10%. You can see that 1.1, 10% every month. So if the rats are plentiful coming back to the owls, this 0.4 R will tend to make the owl population rise, as opposed to decreasing by half each month. It'll start to rise. While the negative term over here in the rat population measures the death of rats due to predation by owls. So we want to determine the evolution of the system when the predation parameter p is 0.104. Here I have my x of k, which is the owls and the rat populations. My x of k plus 1 is the owls and the rat. And then I write my equation, which O of k plus 1 is 0.5 k plus 0.4 R of k, and minus my predation factor, which is 0.04 O of k, and my 1.1 R of k. So I can convert this into my matrix equation. So I have my 0.5 here. My predation on the owls is negative 1.04. Then I have my 0.4 for my rat population, and over here for my rat I have 1.1. So you can multiply this out and see that you get these two equations. Once you have verified that, to find my eigenvalues, I'm going to take the determinant of A minus lambda I, and here I've written it out where I have lambda equals 0.58 and lambda 2 is equal to 1.02. And I'm also just going to tell you to help me with my algebra. I was able to do my cross multiplication here and then minus the cross multiplication here. But to help me to get to this point, I used Wolfram Alpha. So if you go online, you type wolframalpha.com, you type in your equation. I substituted x for lambda because, I don't have a lambda on my keyboard, but I typed my equation in, and then what it gives me, it outputs these alternate forms. So I chose first to express it in, this quadratic form. And then it also gave me the roots. So when I talk to you about using Wolfram Alpha to do my algebraic calculations or maybe some other repetitive calculations, this is what I'm talking about. I'm talking about this website here, wolframalpha.com. Now that I have my eigenvalues, lambda 1 is equal to 0.58 and lambda 2 is equal to 1.02, I can find my eigenvectors. So for lambda equals 0.58, you can see I have my A minus lambda I minus 0.58, and I get the matrix minus 0.08 minus 0.104, and the second column vector is 0.4, 0.52, and since I'm solving the homogeneous equation, my augmented matrix has 0, 0, and I do the matrix row reduction, and I get the x1 is equal to 5x2, so my first eigenvector is equal to 5, 1. Similarly, for lambda 2 equals 1.02, I get v2 is equal to 10, 13. And actually, just to let you know, I got x1 is equal to 0.77 x2. And I chose to make, actually I chose a different one, but I looked in your book and 10, 13 was a very clean way of doing this as opposed to 1 and 0.77. So I've summarized my work so far over here, ending with my eigenvalue 1 and eigenvector 1, and my eigenvalue and eigenvector number 2. I can write then my x naught, which was not given to me, but an x naught is equal to c1 times my first eigenvector and c2 times my second eigenvector. And I just kept my eigenvector, the first eigenvector is 5, 1, and my second eigenvector is 10, 13. Then x1, when I take my next iteration, moving forward in time by 1, I am going to get c1 lambda 1 v1 plus c2 lambda 2 v2, and that will give me c1 lambda 1 squared v1 plus c2 lambda 2 squared v2. The details of the calculation are here, and also these details we had worked out before when we did our general equations up here. And then kind of extrapolating to x of k, just as we had done previously, I'm going to get c1 lambda 1 to the k v1 plus c2 lambda 2 to the k v2. So I'm going to get c1, and my lambda 1 is 0.58 to the k times v1, 5, 1, plus c2, my lambda 2 is 1.02 to the k times my v2, 10, 13. And just a note, we could have gone straight here from this formula here, but I have to admit, I really don't memorize the formula. I just kind of know that I can plug in x1 and x2 and see the pattern and quickly derive the formula for x of k because I don't like to memorize too much. So this part right here is the solution that will help us analyze the long-term behavior of the system. So as k approaches infinity, we already mentioned that our 0.58 raised to the k is going to approach 0, whereas if c2 is greater than 0, then for all sufficiently large k, x of k is approximately just equal to the c2 times 1.02 to the k times v2, which is 10, 13. And this approximation says that eventually both entries of x of k, the number of owls and rats, grow by a factor of almost 1.02 each month, a 2% monthly grow rate. X of k is approximately a multiple then also of 10 and 13. So the entries x of k are nearly the same ratio to 10. to 13. That is, for every 10 owls, there are about 13,000 rats. And one more point, in the dynamical system where we have x of k plus 1 is equal to a x of k, where a is n by n, and its eigenvalues satisfy the condition that lambda 1, the first eigenvalue, the magnitude of the first eigenvalue is greater than or equal to 1, and the magnitude of the other eigenvalues is less than 1, and v is the eigenvector corresponding to lambda 1. If x naught is a linear combination of the eigenvectors with c1 not equal to 0, then x of k plus 1 is approximately equal to lambda 1 x of k, and x of k is approximately equal to c1 lambda 1 raised to the k v1. When A is a 2 by 2 matrix, we can supplement our algebraic considerations up here with a geometric description. We will view the equation x k to plus 1 equals a x of k as a description of what happens to an initial point x naught as it's transformed repeatedly by the mapping x goes to ax. So the graphing of the sequence x naught x1 up to xn is called a trajectory of the dynamical system. So that's what we'll be doing. We'll be graphing the trajectories. This here is a summary of what we will find that we will work up to through a number of examples. So here I have my definition of trajectory and the summary here that we are working up to. So our first example is to plot several trajectories of the dynamical system where x of k plus 1 is equal to a x of k, where A is the 2 by 2 matrix with column vectors 0.80 and 0.64. We start by looking for eigenvalues, but since A is triangular, that's fairly straightforward. It's the diagonal. So we have 0.8 and 0.64. So A minus lambda I is going to be 0.8 minus lambda and then 0. And our second column vector is 0 and 0.64 minus lambda. So when we look for our eigenvectors next, we start with lambda, our first eigenvalue. Lambda is equal to 0.8. Plugging that into our equation a minus lambda I x equals 0, we get this augmented matrix here, which tells us that x1 is free and x2 is equal to 0. So for our eigenvector to represent our representative eigenvector, then for lambda equals 0.8 is going to be 1, 0. Similarly, for eigenvalue 0.64, we plug into our augmented matrix. We're going to get x1 is equal to 0 and x2 is free, so our eigenvector associated with 0.64 is going to be 0, 1. Then my x of k is equal to c1, 0.8 to the k, 1, 0, plus c2, 0.64 to the k, 0, 1. As k approaches infinity, this here goes to 0 because of this 0.8 to the k, and also this 0.64 to the k will go to the 0 since the magnitude of both of these is less than 1. So that means x of k goes to 0. So this is here, the originator is an attractor when both eigenvalues are less than 1 in magnitude. And let's look at the way it approaches 0. We'll look at the graph. I have summarized what we found over here. We have our eigenvalue 0.8, eigenvector 1, 0, eigenvalue 0.64, eigenvector 0, 1. So I've written a starting point, x naught equals 3, 3. In terms of my eigenvectors, that's easy, 3 times 1, 0, plus 3 times 0, 1. So then x of k, if my starting point is 3, 3, is 3 times my eigenvalue 0.8 to the k times my eigenvector 1, 0, plus 3 times my eigenvalue 0.64 to the k, 0, 1. And what I have done is I've written k here, and then I wrote my coordinates x, y. So x being my 3 times 0.8 to the k times, well, the 1, that gives me my x coordinate. And then my y coordinate is 3 times 0.64 raised to the k. And I started with, k equals 0, and I got 3, k equals 1. So that's 3 times 0.8 is 2.4. 3 times 0.64 to the 1, that's 1.9. I went on 2, 3, 4, 5, and 6, and then I plotted this, and you can see the trajectory from x naught equals 3, 3 goes down, and it's decreasing towards 0. I did a similar thing with different starting points. So I have the 3, 3 here. I have the starting point negative 3, 3 here. over here I have the starting point negative 3, 3, and here I have the starting point 3, negative 3. So the four corners of the box with edges at 3. And you can see all of these go down. Oh, and then I also have this one here that starts at negative 3, 0, and then one that starts at 3, 0. And you can see everything goes down towards 0. So that's why we say that over here, the origin is an attractor when both eigenvalues are less than 1 in magnitude, as you see is the case. So the origin is an attractor. All trajectories tend towards the origin, and this occurs when both eigenvalues are less than 1 in magnitude, as we have. The direction of the greatest attraction is along the line through 0, and the eigenvector associated with the eigenvalue with smaller magnitude. So our smaller magnitude eigenvalue is 0.64. So the direction of greatest attraction is along this eigenvector 0, 1. So 0, 1 in the y direction. So here will be our greatest attraction. Our next example is of a repeller here. So I'm going to put my arrow. And in particular, it's the 2 by 2 matrix with column vectors 1, 4, 4, 0, and 0, 1, 2. Again, it's triangular, so it's easy to find our eigenvalues, 1.44 and 1.2, and then we can solve for our eigenvectors. So for 1, 4, 4, our eigenvector is 1, 0, and for 1.2, our eigenvector is 0, 1. So here, because our general equation x of k is c1 1.44 to the k 1, 0 plus c2 1.2 to the k 0, 1, these two eigenvalues are both greater than 1 in magnitude, so things will be growing. So things will be, the origin is going to be a repeller because both eigenvalues are larger in magnitude than 1. So for the start of the graph, we're going to start somewhere close to 0, not necessarily at 0, because if you have your point 0, 0, then c1 and c2 are 0, and you're going to stay at 0. But something bigger than 0, just a little bit bigger than 0, and you see as you choose a point a little bigger than 0, you'll start to grow away, and this one will grow. The x coordinate will become bigger faster than the y coordinate. So again, the origin is a repeller. Both terms grow. The first term, the x term, grows faster, and the direction of the greatest repulsion is the line through 0 and the eigenvalue of the larger magnitude. So the eigenvalue of the larger magnitude, as we said, that is the one that grows biggest. Our next example is going to be of a saddle. So I'm just going to put my arrow here to the last example. And the example is this matrix D, the 2 by 2 matrix with column vectors 2 and 0. And the second column vector is 0.5. And the question is to plot several typical solutions of the equation y sub k plus 1 is equal to d times y sub k, and show that a solution that the y sub k is unbounded if its initial point is not on the x2 axes. So again, we can find our eigenvalues are just on the diagonal, 2 and 0.5, and then our eigenvectors will be for eigenvalue 2, our eigenvector is 1, 0. For eigenvalue 0.5, our eigenvector is 0, 1. Then we can say y naught is equal to c1, c2. So then y sub 0 is c1 times our first eigenvector plus c2 times our second eigenvector, and y sub k is c1, then 2, our eigenvalue raised to the k, times 1, 0, plus c2 and our eigenvalue 0.5 raised to the k times 0, 1. So we can look at this. Here we have an eigenvalue whose magnitude is greater than 1, and here we have an eigenvalue whose magnitude is less than 1. So as k approaches infinity, this will go to 0, and this will grow infinitely large. So if y naught is on the x2 axis, that is, our first coordinate is equal to 0 here, then c1 is equal to 0, and yk decays down to 0. So let's look at that over here. So I needed to add some arrows to my graph. So if I'm on this axis here, we're going to be decaying down to 0. So now let's look at points that are not along this x2 axis, which actually I often call this axis the y-axis and x1 my x-axis. So let's look at that. So as k gets larger, this term here gets large while this term here gets small. This term here is the y-coordinate of our y sub k. This term here is the x-coordinate of our y sub k. So as k gets larger, x will get large, y will get small. So if we start somewhere here near x2, then x gets larger as y gets smaller. So you see that trend here. X is getting large, but y is getting small. Also near x2, x tends to get larger. In other words, we keep going to the right, but y gets smaller. We keep going towards this x-axis. Here again, if it's negative, our magnitude of x is getting larger while our magnitude of y is getting smaller. Same thing over here. Magnitude of x is getting larger while our magnitude of y is getting smaller. So the idea is our x-coordinate is unbounded, and therefore our sequence of our y sub k, this is not the y-coordinate, but the y sub k is also unbounded. And the origin is a saddle point. Next, we're going to do a change of variables for non-diagonal matrices. And what we find is that if we have a non-diagonal matrix A, it's similar to a diagonal matrix. And the idea of the change of variables is something that will come up more. Actually, we'll see an example of it in the next video. But the effect of doing this change of variable that we talk about over here is that we will decouple our system, and I'll explain more what that means as we go through our example. When we do a change of variable for non-diagonal matrices, we consider an n by n matrix A with eigenvector bases v1, v2 up to vn for Rn, and let P equal the matrix whose column vectors is that eigenvector basis v1, v2 up to vn, and let D be the diagonal matrix with corresponding eigenvalues on the diagonal. And then we have seen in the previous chapter video that A is going to be similar to that matrix D, and A is equal to PD P inverse. We are going to look at this change of variables in terms of our dynamical system, so x of k plus 1 is equal to a x of k. Then we're going to define a new sequence y of k, and this is our change of variables here. We're going to take our x of k and multiply by p inverse, this matrix here, inverted. This is our change of variables where we replace our variable x with our variable y, or equivalently, we can say that x of k equals p y of k, and I'll show you why these two are equivalent. We will start with this y of k equals p inverse x of k. Now we multiply both sides of the equation by p, and we're going to multiply them on the left. And it's important we multiply this on the left by p and this on the left by p because matrix multiplication is not commutative. So now we have p y of k. This p inverse becomes the identity matrix. Now we have x of k. So now we've shown that these two expressions, this y of k equals p inverse x of k, and this expression, x of k equals p y of k, are equivalent. My starting point now is with my A is equal to p dp inverse that we talked about over here, because A is similar to this diagonal matrix where P is the matrix of eigenvectors. And then I also start with my dynamical system equation, x of k plus 1 equals A times x of k. Then I'm going to plug in my P of y sub k here in place of x of k. And then I'm going to plug in for A my P d P inverse. Here I have the identity matrix, so I'm going to be left with P d y sub k. Also from here, since x of k is equal to p y of k, x of k plus 1 is going to equal to p y of k plus 1. So I had that written here. X of k plus 1 is equal to p y of k plus 1. Also on this side, I have x of y of k, which is equal to p y of k, is equal to my p d y of k. So what I get is, when I multiply both sides by p inverse on the left, I get y of k plus 1 is equal to dy of k. Now we are ready to see what I mean when I say that we're going to decouple our system of equations. We can now write this as a vector equation. And just a note, this this is the vector y. So the y1 then is the first coordinate of our vector y. The y2 is our second coordinate of our vector y, up to y sub n, the nth coordinate of vector y. And then this k plus 1 in parentheses is the fact that we're looking at the y sub k plus 1 in the sequence generated y sub k. Then we have our diagonal matrix with the eigenvalues, and then we have y sub k. So again, this is our vector y, and it has our first coordinate, our second coordinate, up to nth coordinate, and this k here denotes the fact that this is the y sub k term in our sequence here. I'm going to do my first multiplication. My y1, my first coordinate of this y vector, y1, is equal to multiplying the row times the column. I get lambda 1 times y1 sub k, and then I have 0 for the rest. And now it's easy to see here what is meant by decoupling. Now my first coordinate now is only dependent on my first coordinate of the kth term. It no longer depends on my second, my third, up to my y sub n term. That's what's meant by decoupling. This is something we didn't have with our x of k term, with our x vector. So the change of variables from x of k to y of k has decoupled the system of difference equations. So the evolution of the first coordinate, for example, is unaffected by what happens to the second, third, up to the nth coordinate, because y1 of k sub 1 is equal to lambda 1 y sub k for each k. Looking at this change of variables, I cleared out some of my space here because I need to make some observations. And the first observation is my equation. X sub k equals py sub k says that y sub k is the coordinate of x sub k with respect to the eigenvector basis v1, v2 up to vn. I'm going to talk more about that in a minute. And then this statement here we had talked about, we can decouple, or what we've done is we've decoupled the system. So our coordinates in our vector are decoupled. We're coming back to this statement. Now y of k is the coordinate vector of x of k with respect to the eigenbasis. So this is essentially why we're talking about change of variables. And do you remember, like in a previous video, we talked about when we did a change of bases, we were basically going to a new coordinate system. So here's kind of a summary what I got from that video, and it's a few videos back. It's about change of bases. But basically we were asking at that video, how do we convert from coordinates relative to one basis to coordinates relative to a second basis? And this is exactly what we're doing here. We have x of k in our regular basis, Rn, and we're then changing over our bases to the eigenvector bases. And we do that by multiplying by p. And remember, when we talked about converting coordinates, we said the key is once you know how a basis is converted, so once you know how the basis is converted, then you know how to convert all the vectors in the space, because all the other vectors are written as a linear combination of the bases. So what we ended up doing is our change of bases matrix, P, was equal to our bases vector in our new bases. So that's essentially what we're doing here. We're forming our matrix P based on our new eigenvector bases. And this is an easy change of coordinates to do because we're going from Rn, so kind of like the standard bases, to the eigenvector bases. So P is specifically going to be the eigenvectors. So if you didn't recognize this earlier, hopefully this little review brought it all back for you. And if not, then the video or the chapter you want to look at is the one where you're talking about change of bases from, anyway, that's it. And so again, the last observation then is I'm making calculations in the new eigenvector coordinate system, and when n is equal to 2, this amounts to using graph paper with axis in the direction of the two eigenvectors. Again, this idea was covered when we talked about change of bases. What we get with this change of change of bases is we're decoupling our system. So I kind of thought after we had talked all about this, maybe your book would have an example, but I didn't see one. But I will tell you that the next chapter, we will definitely be working with this. Last, we're going to do a quick example of eigenvalues, and we will see that eigenvalues with magnitude 1, the iterates of the point x0 spiral around the origin in kind of an ellipse kind of trajectory. And if we have two complex eigenvalues, and remember the two complex eigenvalues are going to be complex conjugates. So if their magnitude is greater than 1, then 0 is going to be a repeller, and two complex eigenvalues magnitude less than 1, then 0 is the attractor. We start with the example. A is a 2 by 2 matrix with column vectors 0.8, negative 0.1, and the second column vector 0.5 and 1. We can find the eigenvalue. The first eigenvalue is 0.9 plus 0.2i, with the eigenvector 1 minus 2i, 1. And then lambda 2, the second eigenvector, is 0.9 minus 0.2i, with the eigenvector 1 plus 2i, 1. Looking then at the magnitude of my eigenvalue, so the magnitude of 0.9 plus 0.2i is going to be less than 1. So if I take a look at my trajectories starting at these 3 points, I get these spirals, things that kind of spiral in towards the origin. So this is my summary. If the eigenvalues have magnitude of 1, then iterates of a point x0 spiral around the origin in an elliptical trajectory, sort of like an ellipse. Two eigenvalues magnitude greater than 1, then 0 is a repeller, and the iterates of x0 spiral outward around the origin, and two complex eigenvalues with magnitude less than 1, then 0 is an attractor, and iterates of x0 spiral inward towards the origin. Now we've completed our material, and I do have one more example for you, but since we've discussed everything, I'm going to suggest after you hear the problem description that you pause the video and give the problem a try before you listen to the solution. The problem is to find the general solution of the difference equation x of k plus 1 is equal to a x of k if x0 is equal to the vector 1, 11, negative 2. The second question is what happens to the sequence of x of k as k goes to infinity. Now A is our 3 by 3 matrix, which is equal to 1/9. The first column vector is 7, negative 2, 0. The second column vector is negative 2, 6, 2. And the third column vector is 0, 2, 5. We are given that the first eigenvalue is 1 with corresponding eigenvector negative 2, 2, 1. The second eigenvalue is equal to 2/3 with corresponding eigenvector 2, 1, 2. And the third eigenvalue is 1/3 with corresponding eigenvector 1, 2, negative 2. And again, our x0, our starting point, is 1, 11, negative 2. So I thought it was kind of nice. We had the eigenvalues, eigenvectors given to us. So the first thing we need to do is write x0 in terms of our eigenvectors. So as a linear combination of v1, v2, v3. So we solve this augmented matrix here, and we find that x3 is equal to 3, x2 is equal to 1, and x1 is equal to 2. So that means x0 is equal to, where we have 2v1, x2 is 1v2, and x3 is 3v3. Then I'm going to have x1 then will be equal to a times x0, which is a, and then I plug in my x0, 2v1 plus v2 plus 3v3, and then I pull out my my scalars. So I pull out my 2, and I have av1. I have my 1 times AV2 and my 3 times AV3. Now because V1, V2, and V3 are all eigenvectors, that means this is equal to 2 times the eigenvalue times V1, and this is going to be 1 times the eigenvalue 2/3 times V2 plus 3 times the eigenvalue 1/3 times V3. And then, of course, you can plug in your vectors V1, V2, V3. So x of k, but this is the pattern here. And then remember, if I wanted, I could calculate x2, and what we'll see is you get the same thing, except now you have your eigenvalues are going to be raised to the second power. And in general, x of k has the eigenvalues raised to the kth power. And if you need to do one more term, the x2, just to see the pattern, that's fine. But eventually you'll get to this pattern. So this is the general solution for x of k. So what happens to x of k as k goes to infinity? Well, here, looks like it's going to stay at 2v1. This here, because it's less than 1, will go towards 0, and this here also, because it's less than 1, will go towards 0. So as k approaches infinity, I said my 2/3 k and my 1/3 to the k approaches 0. So x of k is going to approach 2 times v1, which, where's v1? Here's v1. So it's just 2 times this vector here, which is -4, 4, and 2. This is my kind of long-term solution. To review what we have covered in this video about discrete dynamical systems, we said that eigenvalues and eigenvectors provide a key to understanding these systems that can be described as x of k plus 1 is equal to a times x of k. Such equations are used to model population movements and various Markov chains. And then, as I mentioned, in this video, a lot of things will be done on population because it's easy to understand. There are other engineering applications, but then we'd have to kind of talk about, I don't know, circuits or something. But anyway, the vectors x of k give information about the system as time, denoted k passes, where k is a non-negative integer. For convenience, we're going to assume that eigenvectors are arranged in order of increasing corresponding eigenvalues. And since v1, v2, vn, this is the set of eigenvectors, is a basis for Rn, then any initial vector x0 can be written as a linear combination of our basis vectors. And this eigenvector decomposition of x0 determines what happens to our sequence x of k. And we just did an example of that. But x1 then is equal to a times x0, where x0 is our linear combination, so that would be then a times this linear combination, but we pull out our constants in front. So we have c a1 v1 plus c 2a v2 up to c a vn. But now, because these are eigenvectors, we can, then a vn is just equal to the eigenvalue times vn. And a v2 is the eigenvalue times v2, and a v1 is the eigenvalue times v1. I don't know why I did this backwards, but that's the way it is. And then we could do another term x of 2, but for these notes, I just went straight to x of k. It's going to be the same thing, except now your eigenvalues are going to be raised to the kth power. And then you can look at this. As k gets large, if the eigenvalue, the particular eigenvalue, is less than 1, then as k gets large, it's going to go to 0. If it's equal to 1, then it's just going to stay 1. And if it's greater than 1, then it's going to grow unbounded. That was my alarm, by the way. I know I have alarms for everything. Then the 2x2, since we only need a two-dimensional graph, sometimes you might be asked for a geometric description. So you can view this as equation. You have an initial point x0, and it's transformed repeatedly by this matrix A. So you multiply x0 by A to get x1, and then to get x2 you multiply x1 by A, and then to get x3 you multiply x2 by A. So essentially you get a sequence of x0, x1 up to xn. And if you plot these points, you get a trajectory of the dynamical system. And we call the origin an attractor when both eigenvalues are less than 1 in magnitude. Remember, if the eigenvalues are less than 1, then everything's going to kind of go to 0 because lambda is going to go to 0. Lambda to the k goes to 0. And in this case, we're talking about a 2x2. So that's why it says when both eigenvalues are less than 1. The origin is a repeller when both eigenvalues are larger than 1, because when you raise the eigenvalue to k, it's going to get large. And the origin is a saddle when one eigenvalue is less than 1 in magnitude and the other is greater than 1 in magnitude. Next, we talked about change of variables. So we can consider an n by n matrix with an eigenvector bases, v1, v2 up to vn for Rn. And then our change of bases matrix, then P, could be equal to the eigenvectors, v1, v2, vn. And D is a diagonal matrix with the corresponding eigenvalues. Then we'll see that A is equal to P, D, P inverse. Then if x is a sequence satisfying, it's this dynamical equation, x of k plus 1 is equal to ax, we can define a new sequence where we do a change of variables into using our eigenvectors as a basis. So y sub k is equal to P inverse x of k. And then what we find is then, where is this? That we can decouple our system. Okay, then finally we did examples of complex eigenvalues. When the eigenvalues have magnitude of 1, the iterates of the point spiral around the origin in an elliptical trajectory. When the two complex eigenvalues and the two, they're going to be complex conjugates, so they're going to have the same magnitude. So when the two have magnitude greater than 1, then 0 is a repeller, and when the two have magnitude less than 1, then 0 is an attractor. So that's it for this video. Thank you for watching.